Now, the helical dipole, what's important to know about this is that the peptide bond has a very strong dipole moment. The carbonyl group is going to be negatively charged and the amide is going to be positively charged. All peptide bonds in the alpha helix have a similar orientation to one another. The alpha helix has a large macroscopic dipole moment that is enhanced by unpaired amides and carbonyls near the ends of the helices. So negatively charged residues often occur near the positive end of the helix dipole. Now, what that is actually going to look like is your N termini is positively charged and your C termini is negatively charged. So, excuse me, we almost have an increase in concentration of those positively charged groups on the N termini and a increase in the concentration of negatively charged groups on the C termini. So that's just a facet of what that helix, what that alpha helix ultimately looks like and where that charge distribution ends up being. Now your next, so of the three secondary structures, you got your random coil, which I guess it counts, but it kind of doesn't count, your alpha helix, and your beta sheets. Your beta sheets are the ones that are of adjacent residues. So we'll see why in just a second. Beta sheets are the planarity of a peptide bond in tetrahedral geometry of the alpha carbon create a pleated sheet-like structure. Okay, so this is pleated just like, and honestly, I remember hearing this term for the first time and I was like, pants? You can get pleated pants, and oh yeah, sure enough, that does have a pleated sheet-like structure. Now the sheet-like arrangement of the backbone is held together by hydrogen bonds between backbone amides in different strands. Okay, side chains protrude from the sheet, alternating in an up and down direction. Okay, so this right here is a single strand of a beta sheet. There are multiple strands that make up a beta sheet, but this is just one of them. Now, our groups are either going up or they're going down from one another. Now, what does this ultimately look like? Well, it has two different displays, or has two different presentations. There's the parallel and the anti-parallel beta sheets. Multi-strand interactions are called sheets. So multiple beta strands come together to make a beta sheet. Sheets are held together by the hydrogen bonding of amide and carbonyl groups on the peptide bond from opposite strands. Two major orientations of beta sheets are determined by the directionality of their strands within, and they are parallel and anti-parallel. Parallel sheets have strands that are oriented in the same direction. That might seem a little bit weird because it's like, how do we kind of envision this? And we've got some examples in just a moment. So I think, no, that's not a good. I'm trying to find something on my desk that would work. And I've got this little twist tie, and I'll try to use that, but I'll also just show you pictures and try to describe it that way. Anti-parallel sheets have strands that are oriented in opposite directions. Okay, so parallel, the strands are going in the same direction. Okay, so what that might look like. Let's look at this strand right here. Now, let's say that this is the N termini and this is the C termini. Now, if we had something like this, actually, I'm just going to abandon that because I can't really do that well enough. We'll just move on and I'll draw when I need to. So this is a parallel beta sheet. The hydrogen bond strands run in the same direction. Okay, now hydrogen bonds are bent, and so they're fairly weak. Okay, now what I'd like to draw your attention to and get this kind of same directionality is this would be the N, this is the C, this is the N, this is the C, this is the N, this is the C. And so I know whenever I was first introduced to parallel and anti-parallel beta sheets, I was like, I get the N to C, those make sense to me, but what does that look like? And it's easiest for me to try to imagine, here's my polypeptide. Okay, now if I had something that looked like this, okay, so this is my N termini, sorry, that's my N, and this is my C. Now the directionality of this is going N to C, but what I've got here basically is this is N to C, and this is N to C, compared to something that looked like, I'm going to undo that. I'm going to erase that. Sorry about that. If I compared it to something like this, this is N, this is C. This is my final C of my overall polypeptide, and this would be an N portion of my polypeptide. So this N and the N's line up with one another, and the C's line up with one another. So I'm going to call this model number 1 and model number 2. And I like to see these just because it's helpful for me to see it on a grander scale. So this number 2, this would be an example of a parallel beta sheet. So that means that display number 1 would be a good example of an anti-parallel beta sheet. Now what an anti-parallel beta sheet is, I'm going to go ahead and show you that N and C, N and C, N and C. The hydrogen bonds are basically on top of one another. They're linear. So these are a little bit stronger because they're shorter. So if we actually already kind of talked about hydrogen bonds and their presentation based on if it's angled or if it's straight on. Those ones that are straight on, those are stronger. We talked about that in, I think it was chapter 2 stuff. But what this looks like is something like this. So N, C, N, C. And what I'm doing is I'm just, think about this as, there we go. We've got kind of filler peptide bond that comes in there. So this is all one strand, but these two different strands are positioned, or this is all one polypeptide, but this polypeptide is positioned in 3D space to put these strands running in opposite directions of one another. Now, beta turns occur frequently whenever strands in a beta sheet change direction. A 180-degree turn is accomplished over 4 amino acids. The turn is stabilized by a hydrogen bond from a carbonyl oxygen to an amide protein 3 residues down in the sequence. Proline in position 2 or glycine in position 3 are commonly found in beta turns. We talked about proline and glycine as being highly unlikely to be found in an alpha helix, whereas proline and glycine, because of those same reasons, because proline gives you that abrupt twist and glycine is a very small and flexible residue, they're actually going to help the formation of these beta turns. And now what those beta turns look like is this right here. So this actually highlights, this is amino acid number 1 to 2 to 3 to 4. We've got a proline in position number 2. Because of the structure of proline, this would be our N, this is our alpha carbon, this is our carboxy termini. We can throw this R group outside, and because of that R group's like limited flexibility, it's going to force proline to do this. And glycine in this third position, because glycine has such a small R group, excuse me, it's going to give you some flexibility to enable this second type of beta turn. So a type 1 beta turn is going to include a proline at position 2, and a type 2 beta turn is going to include a glycine at position number 3. Well, that's what we've got so far on chapter number 4. So I hope you enjoyed it, and I hope that was helpful, and let's keep going.